G'day everyone, welcome to Lubrication Experts. We've got Jim back, which was really exciting. So back by popular demand. The last talk that we did on the wind turbine gear oils was really well received, and I had a lot of people clamoring they were for Jim to come back. So we're going to have a little bit of a discussion.
The sound of the din is deafening.
It's a stadium full of people. It's an empty stadium, but it is a stadium. We're going to talk first up on gear oils. Jim's got a lot of experience working with industrial gear oils and formulating industrial gear oils. So would be really good to get a lot of his insights on kind of like the behind the curtain of the industry, if you like. So obviously Jim needs no introduction, so we might just jump straight into it. Jim, just as a very maybe like a fantasy question, let's call it. If you could design a new industrial gear oil today, you had a completely blank slate, and they said, make the best thing that you can. Where would you start, and what would you do?
Wow. That's a pretty wide open question.
Yeah.
But, and the usual response is, that's why engineers hate chemists, because we have two hands. You could say, on the one hand, do you want a wimpy, cheap thing? But on the other hand, you want something that'll last forever and even your grandchildren don't have to worry about, right? So which do you want, right? So I've always been of the opinion that you really want something that'll be as durable as possible, because you never know what's going to happen to a machine in service. It's the number one thing why a lot of industrial lubricants get condemned in service is contamination, or an ancillary failure that causes some kind of a corruption to the sump. So the best hydrocarbons that I could grab, which would be metallocene PAOs as a base. Yeah, and I'm a fan of alkylated naphthalene. I'm a big fan of alkylated naphthalene. I saw your one podcast about alkylated naphthalene and why you love it. For me, it's the ultimate synthetic base stock. A lot of people don't like it because it's got a low viscosity index, but I say, don't worry about that. I mean, what you do is you figure out what viscosity you need for the operating temperature and let her rip, right? So, I had the good fortune of working with ExxonMobil Chemical on a few flavors of alkylated naphthalene for very high alkylated naphthalene content lubricants. And those lubricants were, and still are, quite bulletproof. The SHC Rare series. And we also had the SHC Elite series, which unfortunately I found out got canceled earlier in 2021. But that's what I would start with. I would definitely not use an ester as a co-base unless I absolutely had to. Esters bring with them a lot of advantages, but a lot of disadvantages, right? They're much more delicate than alkylated naphthalene, and they're even more delicate than synthetic hydrocarbons. So, and I'm also a fan of synthetic hydrocarbons versus the heavily hydroprocessed mineral oils. One of the big downsides of mineral oils that are heavily hydroprocessed, I mean, you could get Group 3 base stacks, from processing of Group 1s or Group 2s. But the more you process those base stacks, the less options you have in terms of viscosity, right? And when you're talking about industrial gears, industrial gearing kind of starts at ISO 150 and goes up from there. Worm gears, ISO 460, ISO 680, and you're never going to get there with anything that comes from directly from a refinery in a barrel of crude. You're going to have to get that from some type of synthetic PAO. So
yeah,
that's definitely what I would start with, was PAO and AN in some type of mixture, because obviously none of the additives that we typically work with are mostly soluble in hydrocarbons only. So you need you need a co-base of some sort. So
Yeah. Okay.
um,
Interesting. So maybe if we take a little bit of a detour there into sort of the alkylated naphthalene discussion, um,
okay.
uh, because that's a topic that people have shown a bit of interest in as well. So with esters, when we say that they're delicate, I think usually we're referring to kind of like the hydrolytic stability, right?
Yes.
Because thermal stability seems to be okay in that, like, let's say, for example, they're pretty commonly used in the jet oils. So they seem to
Yes.
operate at high temperatures okay. It's just their susceptibility to water. So with ANs, maybe a couple of questions, because people don't really know all that much about them, to be honest. So in the presence of water, are they pretty much bulletproof in the same way that, like a PAO doesn't really interact with water, would be the first question. And the second one is, what is the breakdown mechanism for an AN when it eventually does fail?
Okay. So the first question is, yeah, they behave like another hydrocarbon. They essentially, I mean, just if I can just take a little do loop on your side detour there about esters and their thermal stability, I agree 100% that they're thermally stable for very high temperature applications, which are also anhydrous for the most part, right? So there's no water. And, prior to my few decades of working in industrial lubricants, I worked in fuel additive and fuel delivery here in the US for about 7 years. And one of the things that you learn about water in general, particularly as it touches fuel supplies or any type of hydrocarbon supply network, at least here in the US, is that water is never pH neutral. It's not ideally pH 7.00. Water has a history of what it has seen pretty much in the liquid form over the previous century of its rolling around the planet. So there's always water that's acidic, water that's caustic, high pH, low pH. You have to consider your operational environment, how you're actually going to worry about that. And the thing about esters is that they're both esters are both sensitive to acid and they're sensitive to base. So that therein lies the problem. You can have a alkylated naphthalene or PAO based base stock in the presence of just about any kind of environmental pH spectrum you could think about, and they just don't hydrolyze. They don't do anything. They just sit there and form two layers eventually. They're mostly insoluble in each other. So that's the first thing about alkylated naphthalenes is that it's essentially a fusion of an olefin, the tail piece, and a fused C10 aromatic ring. So you have something that looks sort of like an octopus with a single tentacle coming out the back, right? So in solution, that's kind of the way they behave. And eventually the degradation mechanism is usually by oxidation at fairly high temperatures. So the thing about an alkylated naphthalene is that you've got the core is the ring structure, and then you've got the tail that's sort of hanging off the side, but there's always the carbon that's next to the benzene ring that the hydrocarbon tail is attached to has a single methyl group and one hydrogen. And that hydrogen is, a chemist would say, is the labile hydrogen. So that's usually where the alkylated naphthalene begins its degradation process. So usually some kind of a hot radical, some type of radical species, or not even a very strong base. Will have to be an extremely strong base, but mostly it's by oxidative radicals that will extract that proton, form a radical, stabilize next to the aromatic ring, and that begins the degradation process. We actually did a bunch of work with the folks up in Clinton before I retired, and we actually looked at the alkylated naphthalene base stocks that ExxonMobil had, and we analyzed the headspace above the solution as we slowly heated a solution of alkylated naphthalene, and then you'd analyze the gases that would come off in the presence of either nitrogen or in an oxidative environment. And by and large, that's what you see. You see the naphthalene come off, and you see the hydrocarbon pieces come off, and there's really not a lot that you tend to see before it begins to degrade. So that's one of the really elegant things about alkylated naphthalene relative to PAO or esters, is that when esters hydrolyze, they form two species of the acid and the alcohol, and with a hydrocarbon, you've got whatever those things look like. But with alkylated naphthalene, it scissions apart, and usually the two pieces are volatile, and they actually leave the either the reaction space, or they leave the operational conditions, which is kind of an elegant solution to a lube that sort of falls apart and doesn't leave any negative residues behind. So I hope that answers your question about why alkylated naphthalene decomposes at a very high temperature, and it decomposes in a fairly predictable way, so that the species that do generate tend to volatilize out. So.
Yeah, that's really interesting, and I guess that points to a little bit about why it's becoming, more popular, not just in industrial applications, but we're starting to see it a bit more in engine oils too, right? And that makes sense, right? If it's relatively stable in the presence of water, and its decomposition pathway is not to form acids and alcohols like an ester does, then I can see that there's some certainly some benefits there. And like we talked about, I think in previous episodes here, I think the prevailing let's say opinion has always been that high viscosity index is better. And you even see that with the API categories, right? As you go from 1 to 2 to 3 to 4, VI increases. And that's really kind of a holdover from more or less the engine oils, where high VI is good, but in an industrial application where your gearbox is more or less operating in a very narrow temperature window, for 98%, let's say, of its operating life, do you really care about VI all that much?
There are some caveats, like the northern tiers, very high latitude wind turbines, for example, or industrial applications, and where there's a lot of temperature swinging back and forth. You do have to worry about low temperature startup versus the actual operating temperature that you have to deal with. But I think you're right. 95 to 98% of the time, viscosity index really shouldn't play into folks' an engineer's decision about what to pick for a lubrication application.
Cool. Maybe another way of looking at this as well is I find, when you talk to a lot of people about industrial lubricants, often people have a sort of a better technical foundation in the automotive lubricants, right? Not only because they're so common and they make up so much volume in our sector, but also because a lot of people that we work with will work on their own car, and so that's probably been their pathway into lubricant technologies, right? The first time you ever really have to deal with a lubricant is when you do an oil change on your own car. So with that, we've obviously got two different, if you like, breeds of gear oils, right? You've got the automotive gear oils and the industrial gear oils. And as a non-formulator, just looking at some of the spec sheets and things like that, they always seem to be quite different, almost like they were had different origins. So a lot of the automotive gear oils will have seemingly have a lot of additives that sort of seem like holdovers from the engine oil world, versus a lot of the industrial gear oils seem to be built differently, let's say.
True.
So why is that? And could you please help explain maybe some of the differences between them?
The quick and dirty on that is that, the automotive formulating tradition, if you will, predates that of a lot of the industrial lubes formulating tradition. So they, the industrial lubricant formulation specificity really didn't start to evolve until the 1940s or 1950s. I actually had some of the pleasure to meet people who were way older than me when I was, before I had any of this gray hair, who were sort of the beginners of that bifurcation around World War II times of very specific industrial lubes. And industrial lubes at that time, in the 30s and 40s, 1930s, 1940 timeframe, they were very simple lubricants. They were essentially just lightly additized base stock for very specific applications. And the automotive world, as it were, had a chance to evolve specifications and make a lot of mistakes and break a lot of machines. And usually when there's a lot of failures in a mechanical device or in a very specific type of mechanical design, that tends to drive specifications, right? And you'll see that with the automotive specifications. They look very odd compared to the very large machinery that is common to industrial lubricants today. There's the famous saying, you have to be careful of the loose nut behind the wheel. And that really goes back to worrying about the driver problem, right? In industrial settings, you rarely have an errant driver. Usually that's the guy that's about to be fired. But in the automotive sector, you have to formulate to the least common denominator, right? The least competent driver, the most abusive roadway, the lowest design quality gearbox and drivetrain systems, right? So that's really what a lot of things like the sulfur phosphorus chemistry that you see. There's people who talk about EP type of additives. That's heavily sulfurized olefins that, essentially just prevent shock loading type of damage. You don't tend to worry about that in high quality industrial gearing. Yet, you could just, I'm sitting here in St. Louis, and there's a road not too, principal highway, probably about a quarter mile away, and I can hear people stopping and starting and screeching and trucks zooming up and down. And those are all like normal operations of, speed, load changes all the time, right? So you could sort of understand why the automotive sector, even though the overall loads are lower, if you will, compared to the industrial type of application. But the operational environments have for over 100 years and continue to be today very abusive environments, even in mild temperature conditions. And then layered on top of that, you've got, the guy in Saskatchewan in January, he's got to try and get his truck moving at negative 40 C. And if he's got to make a delivery down to Key West 3 days later, right, he's got to worry about high humidity and, plus 30 C, so there's that really odd overlay of performance demand environment that goes into the automotive sector, and that sort of tradition that they came out of, which is when you really think about it, do you really need dispersants and detergents all that much in an automotive gear oil? Because they're there to manage combustion byproducts from hydrocarbons, free radicals, the acids, the bases, the nitrates, the sulfides. Those are the things that you don't see in an industrial setting, and you really don't see those in an automotive gear oil. But that tradition of formulating sort of still carries on through today. If you look at the chemistry that goes into an automotive gear oil, a lot of it doesn't really need to be there. But I think there's so many specifications that are built up over so many decades that you're never going to move those out of the way. There's that finite chance that, I really don't know if I take this out of the formulation, am I really going to have a problem, right? So, and that's the issue. You've got in industrial lubricants, you have the luxury of 10, 50, 20, maybe 30,000 users of a specific type of gearbox, right? But in the automotive arena, you've got millions of users of, there was a body count that was done on one of these car and driver magazines I was reading about a month ago, where they counted up, there's over 1,100 different cars that are available in the US for sale, brand new. And then you've got, the fleet that's on the road is anywhere from 11 to 15 years old, and you've got antique cars, and you've got, hybrid cars. So you think about how many cars rotate in and out of just the North American fleet. It could be as many as 15 million every year coming and going out of what's on the road. And then there's 30 different species of mechanical applications. So I get it why the automotive sector is heavily additized and very conservative and hung over, because they have to formulate to the loose nut behind the wheel. That's really the bottom line. So if you want a pithy little say, watch out for that loose nut behind the wheel.
Fair enough. Fair enough. You talked a little bit about the EP additives there, which are if you like, a feature of a lot of gear oils. I know the distinction between like an anti-wear additive versus what is an EP additive. That line sort of seems to get blurred a little bit depending on who you talk to. Just sort of putting different labels on different additives. But it might be helpful to talk about some of the different types, right? So we've got, there's the ZDDP style, which have contained both sulfur and phosphorus. And then you mentioned sulfurized olefins. Then, of course, there's been a slightly big deal in the wind turbine world, at least, over going to no or low sulfur formulations, right? And having mostly a phosphorus base, EP or anti-wear package, whatever you want to call it. So would we be able to talk a little bit about some of the advantages and disadvantages of those, and maybe how they work in service too? Because I don't think that people have a really good understanding of that.
Yeah, so if you go, again, it's kind of handy to look at a chemistry question like that with a timeline. And, I drive my kids crazy because I always go back to World War II, right? That's, I mean, for a lot of people around the world, that was like the benchmark for changes in society, but it was effectively a giant change in the way machines and manufacturing of different materials, chemistry around the world. So if you think about sloppy gears, let's say you're manufacturing gears for a pre-World War II Ford Model T, and you've got a manufacturing tolerance that's plus or minus 1/10 of an inch. No lie, that's probably it. So you got a lot of backlash going on. You got a lot of flop in the bearings. It's standardized parts, kind of like, you can plug and play Legos from, bearings from this manufacturer and gears from this manufacturer, but there's not a lot of precision. And that sloppiness in parts quality, if you will, sort of lent itself naturally to these EP type of additives, sulfurized olefins and whatnot. So when you're dealing with things that have a lot of shock loading and backlash, the sulfurized olefins building up a sulfur-based fat layer, for lack of a better term, on a steel on an iron surface is just perfect for protecting it when you're dealing with not necessarily heavy loads, but intermittent shock loads. And those chemistries are still good for that application. But when you start evolving things to a more precise manufacturing tolerance, again, post-World War II, things are looking tighter and tighter. So specifications go from, say, 1/10 of an inch. I'm sure it's not that bad, but let's say it's just an easy thing too, 1/100th of an inch, and then 1,000th of an inch, or fractions of a 100th of a millimeter, plus or minus, for a gear being ground by a computer these days. So you can predict what a pinion will do to a wheel, and that backlash and that play in there is essentially gone in modern manufacturing. So you don't really need that kind of backlash protection, sloppiness protection. And that's where the elegance of phosphorus-based, phosphate esters, amine phosphates, heterocyclic phosphorus compounds, they put a very thin anti-wear layer on the steel surface, and they do a much better job of protecting heavily loaded, high torque transfer, high speed load transfers in more tightly machined gears and bearings. Now, when you talk about zinc dialkyl thiophosphate, ZDDP, that's an innovation that came during World War II as the ideal anti-wear additive that sort of one chemistry did it all and continued to do it all for decades and decades, and does it today. That's the go-to anti-wear additive. But it forms protective in the microscopic sense. It forms protective layers of glasses, if you will, that form very hard, patchy surfaces on top of steel. You can't see them with the naked eye. You really can't see them with a microscope. You have to, look for these things with very sophisticated type of instrumentation and analytic methods. These type of anti-wear layers are probably good for, say, 85% of most anti-wear protection. It's when you get into the very heavily loaded, very highly loaded gears where you're talking about FCG style scuffing protection. That's when you have a lot of sliding forces. That's where the ZDDPs kind of just don't function all that well. And you get into the more exotic phosphate esters and amine phosphates and whatnot. So in my mind, there's sort of three levels of chemistry to reach for. There's the phosphorus nitrogen compounds that you see in wind turbines that are really good for very heavily loaded gearing, very high precision gearing. And then below that, you'll find ZDDP style formulations that are broadly generic for a lot of things. And then there's the sulfurized olefins and what are called EP, extreme pressure type additives. Those are for the more sloppy, crazy shock loading kind of systems. So, did that help at all?
Yeah, that was really good. And there's actually
quick and dirty.
Yeah.
Just a quick and dirty sort of overview.
Yeah, no, that's great. And there's maybe a couple of questions I'd like to tease out from that, because you mentioned FCG testing, and then we also talked about the sulfurized olefins, and so there's questions I've got about compatibility with metals and things like that about that. But maybe if we touch on the FCG testing first, as an end user of a lot of these lubricants, I think most people's exposure to FCG testing is just what they see on the spec sheet, right? So, they'll see fail stage, whatever, 10, 11, whatever it is. And people use that kind of as a benchmark for, or how good is this thing going to resist, well, let's say scuffing wear, right? That's kind of everyone's limit of exposure to the testing. So if we were to, peek back behind the curtain and look from the formulation side, what is the benefit of FCG testing? Are we all doing it just because it's become an industry benchmark, or is it helpful to inform the formulation? And the reason I ask is because now, when in what is it, the 2020s that we're in now, if you look across different brands of industrial gear oils, let's say an FCG, whatever I'm looking at, let's say fail stage, 10 or whatever, it's almost like there's table stakes, right? Where basically every formulation meets a minimum criteria, and then there's no differentiation beyond that. So it makes it look like every formulation is equally as capable of resisting scuffing wear or whatever it is. So my question to you is, why are we using FZG testing, and how does it help you as someone on the formulation side?
Well, there's an anecdote here in the U.S. We say that there's a title reserved for the guy that graduates last in his class in medical school. And you know what that is? It's doctor, right? The problem is that getting through medical school in the U.S. is so difficult that even if you're the poor schmuck that graduates last in his class with the lowest grades, you're still a pretty good doctor, right? You should be able to solve most problems, right?
Yeah. Just to be clear, because I have a lot of friends who happen to be doctors, and actually most of my friends from high school happen to be doctors. This is always a bone of contention that I have with them, is that you can get through medical school by scoring 51% on all your exams. And I'm not sure that I want to be treated by a doctor who's wrong 49% of the time.
Well, I realize my current audience is an engineer. So in the engineering world, we're used to, the 95% confidence interval.
Yeah.
In the biological world, if they could get an 80% confidence interval, they're almost Nobel laureates, right? So I mean, you have to sort of calibrate, the mission statement there.
Yeah.
What you want, it's like it's as if the FCG scuffing requirement is, as you say, table stakes for a reasonable performing lubricant. And that's scuffing by and large is a, it's a high temperature, high speed failure, right? And that pretty much requires some type of anti-wear protection that's going to mitigate that surface sliding in a tremendous way. The other thing, one other little sidebar about FCG scuffing tests, I knew the guy that, one of the guys that actually was the originator of the test. His name was Klaus Michaelis. He's a professor at the FCG Institute in Munich. Interesting character. All those guys, these guys are, you want to talk about engineers who are out there, really super crazy smart. Anybody at the FCG who's a professor is just absolutely out there. But they're always being criticized in public forums, like, this is a ridiculous gear. This is an absurd operating condition. How could you possibly think that any engineer in their right mind, how could you teach engineering at a prestigious school like this and get away with selling these gears for $1,000 a pop, for something that's about the size of your fist? And the answer is that it's actually a chemical evaluation test before it's a gear test, right? So, and you run into that problem with the FCG micropitting test as well. Micropitting gears are ridiculous. They have crazy kinds of root profiles that nobody in their right mind as a gear designer would put out there as something that's reasonable. But it is a gear test, right? So you're evaluating chemistry in the presence of a real gear operating in a real gearbox, right? So that's the intersection of the two things. You're not dealing with some crazy little pin on disc or, ball on ball or a 4-ball test, you run the risk of isolating. When you isolate the tribological problem too much, it moves away from the actual interference with all the other variables that are operating in a particular application, like a gearbox, for example. And that's one of the things to keep in mind about the FCG test, is that it's in its stripped out form, it's still a pair of gears spinning around, in a gearbox under controlled temperature and load conditions. So at least you have the table stakes, you have the minimum standards to which you can point your finger at and go, you know, if I didn't get an FCG fail stage 11, then chances are it's not going to work well in that little Toyota over there, or that gearbox in General Electric's, steel mill application, or whatever it is, right? So it's one of those specifications that's almost like a quacks like a duck. All ducks quack, right? Quack. Oh, that's not a bear. Quack. That's not a sea lion. Quack. That's not a howler monkey. You got to have something in your list of specifications that says, does it quack like gear oil, right? And the answer is that it doesn't quack like a gear oil. It has an FCG scuffing load specification, right? So, and you can look at any kind of hydrocarbon like that, like jet fuel. Jet fuel is an example, the most fungible hydrocarbon on the planet. And a drop of jet fuel coming out of a refinery in Paulsboro, New Jersey, looks the same as a drop of jet fuel coming out of Adelaide, down under, right? Why? Why is that? Because the specification list has got 32 things on it, and those 32 things are, as tight as an eye of a needle, right? So that when you specify something, that your table stakes do more than just assure your ability to sit at the $10 table or the $1,000 table at the gambling hall, right? It assures that you know what you're doing in terms of what a gear oil is or what a jet fuel is, right? So to me, the FCG test, it is table stakes to get you to like stage 11 or something like that. But like with wind turbine oils, they are all past stage 14. Each stage is 20% more load than the previous stage, right? So if you look at a stage 14, that's almost double the load of stage 10. And there's some discussions there. The FCG Institute is going to go beyond stage 14 at this point to assure, higher and higher loads. I don't know if that's really going to happen or not, but once you get into specifying high scuffing protection, hot like wind turbine oils that we had talked about previously, high scuffing protection, high micropitting protection, almost ensures that you're going to struggle with good bearing performance, roller element bearing performance, which is extremely important. So then you got the Bermuda Triangle, for lack of a better term, the critical, the three legs of the stool that are most important: scuffing, micropitting, and roller element bearing. So you've got FIG Scheffler, they have a protocol of 4 or 5 tests that are required to, call a gear oil a reasonable gear oil. So, I think it goes beyond just, here's this test, and it's called XYZ. It's you need, if it's called the scuffing test, scuffing is an important failure mode that needs to be mitigated, and it's actually a protocol that you could use to say, okay, I'm protected up to a certain operating temperature, and then the lube fails. And that's kind of the way I would advise looking at the FCG scuffing test.
Yeah, cool. Awesome. As we sort of start to finish up the discussion on gear oils, I always like to end these interviews with a bit of a question about the future. And when we brought up the sulfurized olefins, it started getting me thinking about, compatibility issues with copper, and the fact that, let's say, for example, like the style of gear oil that you can use in a standard industrial gearbox is often not compatible with, let's say, a worm gear drive, right? Because of the yellow metal content on the worm, or sorry, on the wheel. So maybe a question which is maybe geared, excuse the pun, to the future. There's a lot of discussion right now around electric vehicles and new requirements for lubricants that are going to go into electric vehicles. Now, there's discussions about the architecture of an electric vehicle, because that's not really baked in yet, and whether it's a single lubricant system that has to do battery cooling, as well as protecting the motor, as well as protecting the transmission, well, so that's the Porsche style architecture, right? With they had on the Taycan versus, let's say, a Tesla, which is mostly water cooled. There's a whole bunch of, no one's really landed on what is the optimal platform yet. Having said that, it seems like one thing that all the EV fluids are going to have to more or less have in common is protection of the electric motor as well as the transmission. In a lot of electric vehicles, that seems to be a single unit now. And the one of the prevailing issues is that you're trying to design a lubricant which is suitable for, like, it's basically a gear oil, right? Designing it for a transmission, but that is compatible with the copper windings in the motor.
That's a tough mission.
Now that seems to kind of lend itself to a little bit of a discussion on the additives as well. For people that don't really have a firm grasp on why is this such a hard problem, could you please help maybe point out, why that's a difficult thing?
Wow. Yep. The basic thing is the copper, right? So you touched a little bit about worm drive applications. I mean, one of the key things about a worm gear is it's copper alloy of the wheel. So in the case of a worm gear, torque is put into a helical structure called the worm, but the receiver is the wheel. And these gearboxes have a lot of advantages, right? They're very quiet compared to steel and steel gearing. Very compact. You can get tremendous reduction ratios, 100-to-1 reduction ratio in a single contact in a very quiet gearbox. So you tend to see them, used a lot in human contact applications like escalators, elevators, assembly line applications where humans are putting things together and things are moving past them. Those are all dominated by worm gears and whatnot, and other applications as well. And those applications are sort of the vanguard of leading that chemistry question away from the older style sulfur phos chemistry. You put sulfur phos chemistry into a worm drive gearbox, and you'll essentially destroy them. The sulfur gets very reactive. Sulfur in the periodic table is right underneath of oxygen. So chemists always go back to the periodic table. Sorry about that, but oxygen, there's an old saying, rust never sleeps, and neither does thiodation. Oxidation is oxygen adding on to things and oxidizing things, but sulfur right below it reacts in a very similar fashion that oxygen does. And if it's slower, it's different, but it's a very similar process. If you look at silver, for example, silver will turn black if you let a pure silver coin or a piece of silverware sit in an atmosphere, in a household. It will eventually turn black over a short period of time. And what's happening is that all the free sulfur that's in the air is reacting with the silver and forming silver sulfide on the surface. And copper and silver react in oxidative conditions and sulfidation conditions in a very similar fashion. So sulfur will, under ambient conditions and under higher temperature conditions, readily react with things like silver and copper. And copper itself, it has a fairly low oxidation potential. So that's a chemist's way of saying that it will readily react with oxygen in the presence of water, atmospheric oxygen. Just take a copper penny and put it into a cup of water for a week and let me know how green it is. And that green is the beginning of copper oxide, cuprous oxide and then cupric oxide, two different oxidation states that are common for copper. So that therein lies the clue as to what copper is. An ideal conformal metal. It's great for things like worm gears. Sorry, my phone is doing funny things here with one of my children in New Jersey is having a fit. So sorry. So copper will readily react with sulfur, and copper also readily reacts with oxygen. In fact, the copper is not found in the environment unless it's in the +2 or +1 oxidation state, right? So you look at the famous American image of the Statue of Liberty. You know, when the Statue of Liberty was brand new 150 years ago, it looked like a bright copper penny. But sitting there in the harbor, it's turned green, right? So that's copper oxide forming on the surface. And all copper will do that in the presence of atmospheric conditions. And you put it in an electric vehicle, copper is a perfect conductor. It's a relatively inexpensive wire, right? If you really wanted to make a great wire, you'd make it out of silver, but then that's 10 times the cost, right? So copper is readily available for wiring applications, and it will be relatively stable over a long period of time if you protect it. But now you put it in an electric motor, and you start developing rotors and stators, right? So these electric fields get generated, collapse on a microsecond time basis, you know, in these motor controller applications. They have to be naked copper. They have to be fully exposed copper metal. And that fully exposed copper metal is now not only subject to all this atmospheric nonsense that every other piece of copper is subject to, rust never sleeps, but also you've got these electric currents. You know, when you have single electron transfer processes where you've got DC currents, put a DC current on something, positive and negative, it's going to just look at the terminals in your car battery. You can see one turns greenish white and the other one will turn whitish green. And that's simply the oxidation reduction of the electrons moving through a DC battery. Most automotive applications are DC. Now, when you deal with electric vehicles, they have an AC/DC, you know, who knows what the protocol is with electrical generation and these different things. So when you start throwing in stray currents that are doing work in an electromechanical device with exposed copper, now all of a sudden you've got a recipe for disaster. It's another problem that has to be mitigated for lubricant folks. You know, you've got to figure out a way to not only protect, like we've done for a century now, protecting bronze, roller element bearings, cages, wheels in worm gears. We've figured out how to do all these things. Now you add to that the lubricant that's going to protect the gearing system, and it's going to somehow cool off a hot electrical transfer operation. That's a whole nother mission for the chemistry to do, right? You've got all these, as a chemist, I look at the copper in these electric vehicle systems. I see all this electric current going back and forth. To me, I see electrons moving like a swaying breeze on a grass field of electrons moving through these wires, doing all these different things inside of an electric vehicle. And you've got the overlay of all the normal jobs that lubricant's supposed to do for that motor or gearing system. And therein lies the problem, is that copper is a very sensitive metal. And now you're putting it into not just the normal suspects of gearing abuse, but you're also putting a whole bunch of electrical demand on that copper in the presence of all this load and temperature. So you've got this swirling intersection of variables that have yet to be wrestled to the ground. As soon as there's a single configuration, you know, most children can look at a fish and say, that's a fish. It's not a flamingo, right? So once you decide what an electric vehicle looks like, you know, in terms of its anatomy, you know, all fish look like fish, and pretty much most of them are. So once the electric vehicle people become more like fish, then we can sort of figure out how to optimize the chemistry. But if you've got the Porsche methodology, you've got the Tesla methodology, you've got, what is it, LG, who makes the Chevy Bolt for GM here in North America. You've got a whole different kettle of fish going on with Kia and Hyundai. I mean, I try to read about these things, but as soon as I do, my mind blows up. I'm like, you could easily make a map of 7 or 8 different methods of using a DC battery to make this car go. And it's all the nuts and bolts of making the electrons and the gears do whatever they got to do. But my take on this is, keep it as simple as possible. The gearing systems, the automatic transmissions, the manual transmissions, all that's been known forever and ever. Isolate the gears from the electric motor, and then you can easily start to solve problems. Don't try to just smash it all together. That's one of the problems with a guy like Musk. He's I don't need that 100 years of wisdom from General Motors or Ford or any of these people. I'm just going to make a whole new car here in Southern California. Well, I don't know. Have you really looked carefully at a Tesla? The bodies are shit, right? They really don't know how to build the body of a car, and their recalls are through the roof. For most of it is build quality. They're getting that together, but it's the kind of thing where if you want to go faster and you want to go more reliable, use as much that's known, that's already been worked out, before you start getting exotic with saying, oh, if I only had this one lube that did everything. That's the problem with the Swiss Army knife, right? Swiss Army knives can do everything, but they do nothing perfectly.
Yeah.
Right. And therein lies the rub. You're never going to get a Swiss Army knife that you could perform an appendectomy with, right? You need a scalpel, right?
Yeah.
I'm just throwing out examples.
No,
Maybe I'm rambling too much.
No, that's great. Well, that seems like a great place to stop the gear oils discussion. So Jim, really appreciate your time, and
Sure.
yeah, we'll obviously talk soon.
Yeah, electric vehicles, man, that's going to be fun for chemists and engineers in the next 2 decades, man. That's going to be an exciting place to be.
Yeah.
So buckle your seatbelt and plug in your battery.
All right.
All right, man. You take it easy, Rafe. Bye.
Thanks.
Or